26, page 189, talking about rational functions and asymptotes. All right, rational function. What's a rational function? What's something that's rational? What? It can, yes. Rational was something that was either terminating or repeating because it had to be both non-terminating and non-repeating for it to be irrational, yes. Root word of rational is ratio. What's a ratio? Fraction, yeah. So when we're talking about a rational function, we're just talking about a function written as a fraction. And so they tell me here that a rational function can be written in the form of f of x is equal to n of x over d of x, where n of x and d of x are each polynomials. So it's basically just one polynomial divided by another. And n of x and d of x have no common factors. Now, typically when you start working with a problem, the first thing you would do is simplify it down so that it was as easy as it possibly could be to work with. But in these rational functions that we're going to be utilizing, it is pivotal that you make sure that you have no common factor that you could factor and cancel to simplify that thing down, because it literally could lead you to the wrong answer if you did not do that first. Okay? So rational function, one polynomial divided by another where they have no common factors so that it can't be simplified down any further. So an example of that would be like f of x is equal to 1 over x. That's one polynomial divided by another. They have no common factors that can be simplified down. All right? So they ask me, for example number 1, for this function, find the domain of f of x is equal to 1 over x and discuss the behavior of the function near any excluded x values. Okay? So domain. We've talked about domain repeatedly. Your domain is going to be all real numbers unless one of two things happens. What are they? Negative under a square root or a fourth root, right? Like negative under an even indexed radical. What's the other one? Zero in the denominator, all right? So what's my problem here? Zero in the denominator, right? I don't have a radical to worry about. So my domain is going to be all real numbers except for where my denominator is equal to 0. So my domain is going to be all real numbers except for 0 because that's the only place that my denominator would equal 0. Alright, then they asked me to discuss the behavior of the function near any excluded value. So we just want to go through and do a little bit of exploration. If my function is undefined at 0, if that has to be excluded from my domain, then I want to go through and say, okay, as I'm approaching 0 from the left-hand side, what's my function doing? So if I were approaching it from the left-hand side, I might use values like -2, -1, -1/2, -1/10, 1/100th, 1/1000th. I want to get closer and closer and closer and closer to 0 just to see what's going on. And so that's exactly what they've done here. They've given me a table where they've told me the x values that they want me to use, and they want me to come up with the y values. So I can go through and say, okay, if we have -1, and then -1/2, -1/10, -100th, 1,000th, and so on. So if we plug those values in, like let's start with -1. If I take -1 and I put it in the place of x, what do I get for that function? -1. How about if I plug in -1/2? -2, right, because if you have 1 divided by 1/2, that's the same thing as 1 times 2 over 1, right? And it was positive divided by negative. How about -1/10? That would be 1 divided by 1/10. So, right, 1 divided by 1/10 is the same thing as 1 times 10 over 1. And 1 positive and 1 negative, so -10. 1 divided by 1/100th. Yep. And then -1/1000th. So, we start to see a pattern here, right? Where as we're going, the smaller these numbers get, the bigger these numbers get, right? So the closer and closer and closer that I get to x, the bigger and bigger and bigger these y values are getting down here. So how could I express that? We could say that f of x is approaching what? Infinity, right. So if I had kept going with this, like it's almost as if every time I add a 0 up here, it adds another 0 down here. So it would kind of lead me to think, hey, if I kept going and I did 0.0001, I'd get 1.0000. So the closer and closer and closer I get to 0, the smaller and smaller and smaller I make this decimal, the bigger and bigger and bigger this y value is. And so I could say if those y values are going 1, 2, 10, 100, 1,000, 10,000, 100,000, a million, a billion, a trillion, yeah, those values are getting larger and larger without bounds. So the way that I can express that is by using infinity. And every single one of them was negative, so I could express that as negative infinity. All right, let's look at what happens as I approach from the positive side, from the right-hand side. Same idea. If I came over here and I was approaching 0 from the right-hand side, I would use values like 1, 0.5, 0.1, 0.01, 0.001, same type of thing, and you'll see those same values again here in the table that they've given us. We want you to use these x values so that as we get closer and closer and closer to 0 with our x values, what are our y values doing? All right, so if we plug positive 1 into this, what are we going to get? If we put in positive 1/2, what are we going to get? If we put in positive 1/10, what are we going to get? It's just the exact same numbers, right? It's just that now I've got a positive divided by a positive, so each of my answers is positive. So again, as x is getting closer and closer and closer to 0, what is my y value getting closer and closer to? Infinity, right. So if I want a succinct way of expressing what just happened there, I could say that as x approached 0, and this little minus sign right here is representative of, we looked at, you could approach 0 from the left-hand side or you could approach 0 from the right-hand side. That's what these little symbols mean right here. If I approach 0 from the left-hand side where the negative numbers are, or if I approach 0 from the right-hand side where the positive numbers are. Easy way to remember that. So as I was approaching 0 from the left-hand side, for my x values, my y values went to negative infinity. As I was approaching 0 from the left-hand side with my x values, my y values went to negative infinity. All right. Similarly, this one says, as x approached 0 from the right-hand side, those y values approached positive infinity. As my x values approached 0 from the positive side, those y values went to positive infinity. So this just gives me a concise way of writing the behavior that was going on as I approached 0 from both the left-hand side and the right-hand side. That notation is something that we're going to use in Chapter 12 with something called limits, and we're going to use it nonstop next year in calculus. So that's why they go ahead and kind of expose us to that notation here. If you look at the graph kind of shows us the exact same thing. If I graph 1 over x, this is what that graph looks like. And sure enough, as I approach 0 on this graph from the left-hand side, my graph is going merrily along, everything's fine, and then all of a sudden it makes this drastic turn and it shoots straight down. And it goes to negative infinity. Same thing is true as I approach from the right-hand side, everything's going merrily along, and then all of a sudden it shoots straight up. We've seen that before, right? When your graph is going along and then all of a sudden it just makes a hard left turn or a hard right turn, it's usually because what's there? Getting closer and closer to something without crossing over it. What is that? An asymptote. It is possible to cross asymptotes, but most of the time we don't. So, sure enough, from our study of exponential and logarithmic functions recently, we also would recognize asymptotic behavior. And so we can look at that and go, okay, my graph curves suddenly up and it curves suddenly down. That leads me to think there might be a vertical asymptote there. And the definition that they give us over on page 190 for a vertical asymptote says exactly what we were working with right here. It says the line x equals a will be a vertical asymptote of the graph of the function if f of x approaches infinity as x approaches a, or if f of x approaches negative infinity as x approaches a. So if your graph suddenly shoots off to positive infinity or shoots off to negative infinity at some value, it's because that value is a vertical asymptote. And so x equals a would be a vertical asymptote anywhere that happened. Now, we've also worked with horizontal asymptotes. And if we go back and we look at this function, we can see, you know, the graph was going merrily along and everything was fine, and then all of a sudden it leveled off as well. Same thing over here, the graph was going along and all of a sudden it leveled off again, and that was because we had a horizontal asymptote there at 0. So how would I discover that? Well, I could discover that by saying anywhere that x goes to infinity and it approaches one specific value as it does, it levels off on one particular y value, that one particular y value is going to be a horizontal asymptote. Similarly, if my function was going along and all of a sudden it leveled off as I approached to negative infinity, if it leveled off on one particular y value, that y value would be a horizontal asymptote. And so they say as x approaches a positive infinity or a negative infinity, if your y values level off and they approach one specific value, like in our case here it approached 0, then that value is a horizontal asymptote. And so those are the two formal definitions that they give us on page 190 to go along with the kind of common sense logical things that we've been doing with horizontal and vertical asymptotes in our graphing already. The reason they give you those formal definitions is because those are the definitions that we're going to need next year in AP Calculus to justify, hey, I say there's a vertical asymptote here, here's my proof of why it is, here's my justification. Okay? But for our intents and purposes today, if you want me to do 15 homework problems tonight and you want me to tell you where the horizontal and vertical asymptotes are, could you please give me a practical way of doing that? Absolutely. And so now that we've got those definitions and we kind of see where they're coming from and we've done some exploration, let's be practical and look at what are some fast, easy, convenient ways that we can find horizontal and vertical asymptotes. All right? If you have a rational function that has no common factors, you can find your vertical asymptote by setting your denominator equal to 0. So where your denominator equals 0, set that equal to x, and that will be your vertical asymptote. So let's say that we've got example 2 down here. F of x is equal to 2x over x squared minus 1. And they said find the vertical asymptote. All I'm going to do is take my denominator, x squared minus 1, and set it equal to 0 and solve it. So what would I get if I solve that? 1 and negative 1, right. So if I add 1 to both sides, take the square root of both sides, I'll get plus or minus 1. Or if I look at that as a difference of squares, x plus 1, x minus 1, I'd get x equals 1, x equals negative 1. Those are going to be my two vertical asymptotes. If you threw that graph into your calculator and graphed it, you would have a vertical asymptote at x equals 1 and x equals negative 1. And please be sure that you tell me x equals 1 and x equals negative 1, not just 1 and negative 1. 1 and negative 1 are points. X equals 1 and x equals negative 1 are lines. Same thing with my horizontal asymptotes as well. Be sure you give the whole equation, not just the point. All right, then how can I find a fast, easy way for finding my horizontal asymptotes? Well, for my horizontal asymptotes, I'm going to need to compare the degree of the numerator with the degree of the denominator. I'm going to compare the degree of the numerator with the degree of the denominator. All right, so the degree of the numerator they're calling n, and the degree of the denominator they're calling m. You can see that up here. Here's the degree of the numerator n and the degree of the denominator m. Okay? If the degree of the numerator is less than the degree of the denominator, you will have a horizontal asymptote, and it will be y equals 0, no questions asked. If the degree of your numerator is larger than the degree of your denominator, you will not have a horizontal asymptote, no questions asked. If the degree of your numerator equals the degree of your denominator, you will have a horizontal asymptote. And it will be y equals the leading coefficient of your numerator over the leading coefficient of your denominator. That's what they're referencing in the a sub n and the b sub m that you see there. They're going back to the leading coefficient of the numerator over the leading coefficient of the denominator. All right, leading coefficient, remember, is the coefficient or the number out in front of the variable that has the highest exponent. It does not always have to be the one that comes first. They will intentionally try to trick you and make it not the one that comes first. Okay? So you might want to go through and put your polynomials in descending power order if they're not given to you that way. If they give you something like 1 minus 3x plus x squared, you might want to turn that around where you've got the x squared out in front and then the x to the first term and then the constant term, so that it's in descending power order so that you can clearly see the number out in front of the highest ordered variable that's your leading coefficient. Okay? So let's look at an example of each of those. Going back to this example, if they ask me to find my horizontal asymptote, I need to look at the degree of the numerator and the degree of the denominator. What's the degree of my numerator? 1. What's the degree of my denominator? 2. So when the degree of the numerator is less than the degree of the denominator, do I have a horizontal asymptote? Yes. What is it? Y equals 0. Yes. All right, look at the next one. For the next one, they asked me to find the vertical and the horizontal asymptotes. How do I find vertical asymptotes again? Set the denominator equal to 0. So that's the same denominator we had just a second ago. So it's going to be equal to 0 still at 1 and negative 1. For the horizontal asymptotes, what's the degree of the numerator? 2. What's the degree of the denominator? 2. So if I compare the degree of the numerator and the degree of the denominator, since they're the same, I'm going to say y equals leading coefficient over leading coefficient. So what's the leading coefficient in my numerator? In my denominator? So I'll get y equals 2 over 1, or y equals 2. And again, they might try and trick you by turning that around and giving you something like negative 1 plus x squared or something like that. It's not always the number that's out in front. All right, look at the next one. How am I going to find my vertical asymptote? Denominator equal to 0, right? And that's the same denominator, so it's going to have the same values. Horizontal asymptote, what's the degree of my numerator? Denominator. So when the degree of the numerator is larger than the degree of the denominator, then there is not one, right? All right, look at another example. For example number 3, they asked me to find the domain, horizontal asymptote, and vertical asymptote. All right, so let's start with domain. Your domain is going to be all real numbers, unless you have 0 in the denominator or negative under an even indexed radical. Do you have anything to worry about in this problem? What? All right, the denominator can't equal 0. I don't have a radical to worry about, but I do have a fraction. So I'm going to say, okay, my denominator can't equal 0, so I got to figure out where the denominator equals 0. So let's take our denominator, set it equal to 0. If I solve that, how do I solve that? Add 5. Then what? Yeah, let's subtract 5, and then divide by negative 4. You could also move the negative 4x cubed to the other side. That's fine as well, whatever you want to do. But subtract 5, divide by negative 4, and I've got x cubed is equal to 5/4. So how do I get x by itself? Cube root, right. When you insert a cube root, you don't insert a plus or minus or anything like that. So my domain is going to be all real numbers except for where my denominator equals 0. So it's going to be all real numbers except for the cube root of 5/4. All right, then for B, they wanted to know the excuse me, the vertical asymptote. How do you find the vertical asymptote? Set the denominator equal to 0. So I get 2 for 1, right? Because I already did that. I already know that value. So that means I also already know my horizontal asymptote, or sorry, my vertical asymptote. So my vertical asymptote is going to be x equals the cube root of 5/4, wherever my denominator equals 0. All right, horizontal asymptote. What's the degree of my numerator? 3. What's the degree of my denominator? So since they're the same, what am I going to use? Leading coefficients. And pretty much you could guarantee that in the book they would write this 5 minus 4x cubed because they don't ever like the leading coefficient to be negative. So be very careful that I don't look at that as saying 3/5. All right. I would need to say leading coefficient of the numerator is 3. Leading coefficient of the denominator, -4. So I can say y is equal to 3 over -4, or -3/4. So that's going to be my horizontal asymptote. All right, so let's look at a real world application of this. For example 6, it says a business has a cost function of C equals 0.5x plus 5,000, where the cost is measured in dollars and X is the number of units produced. So if I wanted to find the average cost per unit, I would just take the total cost and divide it by the number of units produced, right? Like if you're making 10 t-shirts and they cost you $50 total to make, and you're trying to figure out the cost for each one, you just take 50 and divide it by 10, and that means each one costs you $5 to make, right? Same idea here. When they're talking about the average cost per unit, it's just the total cost divided by the number you're making. So this was the total cost that they gave me, and they told me that I'm making X units. It's also very similar to when we do the mean, right? For the mean, you do the total and you divide it by the number of units, X. And remember that when we wrote mean, we wrote it as X with a bar over it, and you'll notice the same notation here, C with a bar over it, all right? That is our average cost. So find the average cost per unit when X is equal to 1,000, 5,000, 10,000, and 100,000. Now, I have no doubt that you can plug numbers into formulas. So I just went ahead and plugged those in for you so that we could see them and discuss them. So let's take 1,000 and plug it into that equation. We put 1,000 right there and 1,000 right there. Throw that into our calculator and we get 550. That means that when I'm making 1,000 of these, whatever this product is they're making, when I'm making 1,000 of them, they cost me $5.50 each to make. But when I plug in 5,000 as my quantity, now the average cost is just $1.50 each to make. And when I plug in 10,000, it's $1 each to make. And when I plug in 100,000, they're 55 cents each to make. So we get the idea that the more of these we make, the cheaper it's going to get, because I've already paid my rent, I've already paid my utilities, I've already paid my employees to show up, I've already bought all of the equipment. So while everybody's there and everything's up and running, we might as well make a bunch of these, right? And it would cut my cost. But at some point, I do actually have to pay the rent and the employees and the utilities, so I'm not going to be able to get this cost down to zero. I mean, there's going to be a bottom line where really this is as low as I can go. And so the next thing that they ask me is, what's the horizontal asymptote for this function? All right, so if I go back to this function, what's the degree of the numerator? Degree of the denominator. So since they're the same, I'm going to look at leading coefficient over leading coefficient. So leading coefficient of the numerator, 0.5, and of the denominator, 1. So I'm going to get y is equal to 0.5 over 1, or y is equal to 0.5. So when I graph this, there's going to be a horizontal asymptote at y equals 0.5. That would be like y equals 50 cents, right? Since we're working with dollars and cents. And so they ask me, what does that represent? What is that 50 cents? That horizontal asymptote of 50 cents? The minimum what? Yeah, the minimum unit cost. It doesn't matter if I make 10 billion of these things, I'm not going to get them below that bottom line. So maybe as the business operator, I'm looking at this going, okay, I'm very comfortable making 100,000 of these. My supply is matching my demand. I have all of my shipping and all of my distribution and all of my manufacturing. Everything's running smoothly. In order for me to then jump up to make 500,000 of these, I got to go open another warehouse, and I have to pay all these new employees, or I have to have overtime, or I have to add all of these other components. For what? To shave 2 more cents off or 4 more cents off? Is it worth that to me? Those are the types of things that I need to be able to make decisions about. And so those are some of the real world applications of where this might come into play. Okay? All right. So for our homework tonight, on pages 195 to 196, we are doing 179, 11, 13, 15, 1731, challenge 19. On 13 through 17, it tells you to do several things, and one of the things that it asks you to do is to create a table of values. You don't need to create a table of values for those once you've done those other things. So that's what it means by 13 to 17, no table. Okay?